Hi guys, this is Mrs. Homer, and today we're going to be learning about sex-linked traits. Before we get into sex-linked traits, I want to review sex chromosomes. We looked at these during mitosis and meiosis. These are the chromosomes that are used to determine your gender. So you can either get an XX, if you get two X's, you're a female, or you can get an XY. If you get an XY, you are a male. We always say, if you get a Y, you're a guy. So these sex chromosomes come from mom and dad. Mom has an XX and dad has an XY. So we'd like to answer the question, which one of your parents determines your gender? So if we look at mom's XX, during meiosis, they are going to separate through the law of segregation into two separate eggs, and dad's XY are going to separate into two separate sperm. So we can put these into a Punnett square. And if you notice, when we put mom's X's in the Punnett square, she doesn't get to determine gender. She gives everybody an X. But when dad puts his gametes into the Punnett square, he can give an X, which will make these top two a female, or a Y, which will make the bottom two guys. And so it's actually your dad who determines your gender. Now, looking at these sex chromosomes, we can actually look at the traits that are carried or found on them. So any trait or any gene that's found on an X or a Y chromosome is called a sex-linked gene or a sex-linked trait. So we're going to do some Punnett squares today where we look at some of these sex-linked traits. Now, we could look at the X or the Y, and we're not going to spend a lot of time looking at the Y chromosome. So why not Y? The reason is because the dad passes on their Y chromosomes to their son. It doesn't cross over, it doesn't really segregate. The dad gives their Y to the son, so the son and the dad have the exact same Y. And the dad has the same Y as his dad, who has the same Y as his dad. So pretty much every male in your family line will have the same Y. If your dad has a disorder on his Y, his dad probably have it, you'll probably get it, and you'll give your Y to your son, so he'll get it too. The Y chromosome doesn't affect the female at all. So because it's so simple, we're only going to study sex-linked traits that are found on the X chromosome. So we will call these X-linked traits. So any trait found on the X chromosome is an X-linked trait, and it can affect both a male and a female. Now, we know that males only get one X and females get two X's, so we're going to have to treat them a little differently. So first of all, we're going to look at the X-linked traits for females. They're going to follow the traditional rules, whether it's codominance, complete dominance, or incomplete dominance. We're going to follow traditional rules. She's going to get two alleles, one from mom and one from dad. We're simply going to write them just a little bit differently. When we write out any sex-linked gene or trait, we're going to include the sex chromosomes. So in this case, she has two X's, and each X carries an allele. In this case, both alleles are dominant. So this female is homozygous dominant for the trait. In the second one, again, she's a female. We see her two X's, and she has two different alleles, the dominant allele on the first X and the recessive allele on the second X. So this female is heterozygous. She's still going to have the dominant trait just like normal. Our third female, her two X's are here. She has two alleles still, one on each X, but they're both recessive. So this third combination gives you a recessive female. Notice only 1/3 of the genotypes carry the recessive trait. So females have a 1 in 3 genotype of getting a recessive sex-linked trait. This is going to be a little bit different for males. Males have an X and a Y. They only get one allele for the trait because only the X has the trait, not the Y. Now, they get their X from their mother because the mom is the one who passes on the X chromosome to a son. So any X-linked trait that a male has to have come from his mom. Now, we'll write out the examples just like we did for the females, only this time we're going to have an X and a Y. There's only going to be an allele on the X chromosome. So in this case, the male only gets a capital B. And because he has a capital B, the male will be dominant. In the second case, the male has a recessive lowercase b on his X chromosome, and there's nothing on the X. That simply means that because there's no dominant allele, the male will be recessive. He only has to get one recessive allele to get the recessive trait. These are the only two combinations that a male can have. So 1 out of 2 of the genotypes are recessive. Because of this, males have a higher chance of getting a recessive trait than females do when we're talking about sex-linked traits, simply because they only have one X and they only get one allele. We also want to introduce a new vocabulary word, and that is a carrier. When you're dealing with a sex-linked trait, women are often referred to as a carrier. It's simply the heterozygous genotype. They have a dominant and a recessive allele, which means they have the recessive allele to pass on, but they don't have the recessive trait. Males can't be a carrier because they only get one allele, and to be a carrier, you have to have both a dominant and a recessive allele. So only women can be carriers of recessive traits. Now, we're just going to do a couple examples so you can see how we do these sex-linked traits in a Punnett square. So this is our trait for baldness, where capital H is dominant for hair and little h is recessive for baldness. Here are our parents, capital H and little h on mom's X's and a capital H for dad. So mom has hair, but she's a carrier, and dad has hair. When we fill out our Punnett square, we're going to keep the X's and the Y, and remember the alleles will only be on the X's. In this case, you can see that we have one female that has 2 dominant alleles, and she has hair. The other female has a dominant and a recessive allele, and she also has hair. The first male has a dominant allele, so he'll get hair as well. The last male only has the recessive allele, which means he will be bald. So you got a 1 in 4 chance that your offspring are bald, or a 1 in 2 chance that your son will be bald. Now, you can report the outcome of a sex-linked trait in 2 different ways. You might be asked to report the results by just the percentage of the children. For example, 3/4 of your children in this Punnett square will have hair, where 1/4 of the children will be bald. But we might also ask you to report the results by gender. In this case, 1/2 of the males will have hair, 1/2 of them will be bald, 2 out of 2 or 100% of the females will have hair, and 0 out of the 2 females will be bald. So be careful what you are reporting, whether it's by offspring or by gender. So just one last Punnett square. Again, you can have a variety of males and females. In this case, we have a female that's recessive and a male that is dominant. The female has to be bald in this case, and the male has hair. If you look at the Punnett square, we have kind of a different result here. So if your mom is bald and your dad isn't, none of the males will have hair. Boys, if your mom is bald, you're destined for baldness, I'm sorry to say. So look at the females, though. The females, if dad has hair and doesn't go bald, the females have a 0% chance of being bald. So girls, you're looking towards your dad to see if he has hair, and boys, you're looking at your mom to see if she has hair. That wraps it up for sex-linked traits. Tomorrow, you'll be doing some practice in class on sex-linked traits to make sure that you can do the Punnett squares and predict the outcome. Thanks for listening.